The next step we have is to look at the derived equations and set them up inside the code so that way we can then plot them and solve for answers. So to begin, we're going to want to define a function. We'll define it as the change of mole fraction and temperature of the water and the temperature of the gas. Then we're going to have that be with the respect to the height, and then a random variable n. Now after that, we're going to define each slot in the array. You have the mole fraction, which will be set equal to the first slot in the array, or 0. And then you'll have the temperature of the water, which will be the second slot, or 1. And the temperature of the gas will be the third slot, or 2. Now, you may think we can go right into re-entering the derived equations from before. However, first we need to go over the flow rates, the gas flow rate of the water vapor and the air, and how that relates to the ratio, or not relates, how the ratio of the mole fractions is equal to the ratio of the mole flow rate. So we have the gas flow rate of the water, which is equal to the mole fraction divided by the 1 minus the mole fraction for the remaining portion, which is multiplied by the remaining portion, which is the gas flow rate of the air, times the molecular weight of water, and divided by the molecular weight of air. After that, we have the average mass flow rate, which is equal to the gas flow rate of the water vapor plus the gas flow rate of the air. After looking at the gas flow rate, we need to do the average molecular weight, which is the gas flow rate of the air plus the gas flow rate of the water vapor. That needs to be put in parentheses, which is your average gas flow rate, and that's going to be divided by the gas air flow rate, which is divided by its molecular weight, plus the same for the water vapor, the gas flow rate divided by the molecular weight. And now after the average molecular weight, you have the specific heat of the gases, which is the specific heat of air times the specific heat of, times the mass flow rate of the air, which is then added to the specific heat of the water in gas form. That's how I wrote it. Yeah. Making sure the variables are the same. After that, you have that, which will be also multiplied by the gas flow rate of the water, and that will be divided by your average gas flow rate. Now, after completing that portion, we can get into our derived equations. So first we need to do the mass flow rate of the water, which we used in as a variable in the equations. So you have that being equal to the mass coefficient divided by the gas constant divided by the temperature of the gas times the our earlier defined PV times the temperature of the water minus the mole fraction times the pressure. Now, having that, we can go into the change in the mole fraction, which is equal to our derived equation from earlier, which is the negative packing area times average molecular weight, which is then divided by the gas flow rate average times the earlier described mass flow rate. After that, we have the change in the temperature of water and change in the temperature of gas. First, for the temperature of water, from our derived equation, we have the the packing area divided by the liquid flow rate divided by the specific heat of the water in liquid form, which I defined as capital L, which is then multiplied by the heat transfer coefficient times the difference in temperature between gas and water, then minus the heat of vaporization, the enthalpy of vaporization, after the heat of vaporization, it's times multiplied by the mass flow rate of the water. And then we have our change in temperature of gas, which is equal to the packing area times the heat transfer coefficient divided by the gas flow rate divided by the specific heat of the gas times the change in temperature between gas and water. Now, given we've written our three derived equations again, we'll then want to return the equation after that. Now, the next step, we're going to have to converge the equation. So we're going to go before that, and we're going to have another defined function, which is going to be converge feed of the air, temperature, and mole fraction. and that's going to be set again to the random variable n2. Colon that, and with that we're going to define our exit mole fraction and exit temperature of the gas. So our exit mole fraction is equal to, again, the N2 for the first set in the array, and then the temperature of the gas at exit is equal to the N2 second portion of that. Now, since we define that, within that we'll have to do the global solution and then nest the portion we already written under that defined function. And then with that, we'll have to go back into the previous square and set the solution there equal to none. After that step, we're going to want to have the return of the overall defined function. So we're going to set that to the solution, which is then going to be used with the solve IVP for the initial guesses and help with the derived differential equations. So first we have the change in our function with the change in mole fraction, temperature of the water, and temperature of the gas. Next, we need what it's going to be running to, which is 0, and then the max height, which is z, so 0 to z. After that, we're going to have the our exits as well as the other variable, the temperature of the water, by itself, since it's not one of the exits we're looking at. So we have the mole fraction exit, temperature of the water, and the temperature of the gas exit for the output we want. Make sure that's all good. Okay, then we're going to insert a method. This is optional, whatever you want to use. I want to say it's RK45, which will be used if you don't put anything. We'll use the Radu method, and then since the dense output equal to true, and the sol to zplot. Then with that, I don't think that's what I did wrong. I didn't think I nested that correctly. Return our solution. We'll want the first output for the y exit 0, and then we'll want the last digit of that, which can be used by -1, and then minus the feed for the mole fraction, and then we'll want the temperature of the gas exit for solution, which will be the third component of that, and we'll also want the last piece of that array minus the original temperature of the air feed. With that, we're now going to quickly check it to make sure everything works. We're going to have a converge, feed, air, T, Y. And we're going to put in the exit guesses here. Exit guess, guess, exit guess. See. Unindent does not mention outer indentation. Oh, indented it wrong. Unindent. Didn't spell solve IVP correctly. That would hamper a lot. TW is not defined. What do I have temperature of the water defined as? TW. It's not just TW, it's TW feed. Float argument. Where is that? A number, not a function. So now that we have made sure the converge function works, we're now going to adjust that to the root solver. Root. Nope, not in there. Yep, that works. Giving us the root of the exit values. So then we need to take the last step and plot each of the three things we were deriving for as graphs. So first we're going to make a figure. We're going to set that equal to the make subplot plotly. Make subplots. We want 3 rows, 1 for each variable. 3 and 1 column. Next, we're going to want a fig and add scatter. Our x equaling our height, and our y in this case is going to be the first in the solution array, which is the mole fraction. And then we want all of those, which is the same as colon. Given that, we then will name the graph for the mole fraction of water. And we're going to set the rows equal to 1 and the columns equal to 1 as well. And closed it. We're going to make this simpler for doing the next two and copy that one and make small changes. So again, the fig at scatter plot, this time you want the second part of the array, and that corresponds to the temperature of the water, and the row is going to be second. Again, we're going to do this, and we're going to have the third part of the array, which is going to be the temperature of the gas, which is the third row. Running that, made a mistake. Z-plot, not Z. Add that to each of these lines. Should, oh, a whole lot of stuff. Mess up. What did I mess up? Rows, make subplots. Rows equals 3, columns equals 1. Fig add scatter. X equals Z plot. Y equals sol 0, 1. Rows 1, column 2. Doesn't look like that. Invalid. Okay, now that the graphs came out, we can kind of get an idea how it looks. However, it's not the greatest view of it, so we're going to change the view by fig update underscore layout, and we're going to set the width and height differently to 600 and the height to 900. Again, coming up with our graphs, a little more visible. We can see the mole fraction graph going from the 0.25 to around 0.16, and then our temperature of water from about 340 to 300, and our temperature of gas a little over 300 down to 298, a little above that. You can see how all of them slowly decrease over time within the cooling tower.